approximation here is gonna be what? The area of the first one is gonna be delta x over 2 times small base plus big base is what? F of x0 plus f of x1. You guys see what we're talking about right here? This space right here is the height right here, right? This is f of x0. This is f of x1. First one. Similarly, the area for the second trapezoid right here is going to be, again, delta x over 2. This is the height over 2. What? F of x1 plus f of x2, and keep going all the way to the last trapezoid, which is delta x over 2, f of xn minus 1 plus f of xn. Okay? Now we can factor out the delta x over 2 to common factor. Okay? And we're going to group those, combine all the like terms. F of x0, f of x0, right? And then f of x1 plus f of x1, f of x2, to the end. So you're going to have 2 times f of x1, because you got f of x0 plus f of x1 and plus f of x1 plus f of x2 and plus f of x2 plus f of x3 plus data all the way to f of xn. So in other words, all the xi I run from 1 to n minus 1 you have twice, okay? Except for the first term and the last term. So f of x0 twice of f of x1, 2 times f of x2 plus data all the way to 2 times f of xn minus 1, and then plus just f of xn. And this is the formula for the trapezoid root. And as usual, the bigger, the larger the number of n's you have, the more work you do, more trapezoid you use to calculate, the better the approximation you're going to have. Okay? And same idea to calculate the area as before. F double prime of x is less than or equal to k. Okay? Then the area for the trapezoid trapezoid roots, I just keep saying that we're wrong. Trapezoid root is what? Less than or equal to be more exact. Less than or equal to k times b minus a to the third power divided by 12 times n squared. Okay. So you see, this is pretty similar to the previous method of the midpoint rule. However, the error here is twice bigger, and this is divided by 12 n squared. But the previous method divided by 24. Okay. But the disadvantage is the error may be bigger. The advantage is you don't have to calculate a midpoint, so you just use x run from 1 to n, x1, f of x2 all the way to xn. So less calculation on the x term, and in return you got less accurate on the error. So it's up to you to choose. I'll just show you the method. Of course, the way to approximate is the same thing. You have a function, right? You can take derivative, second derivative, and then you find the k. Make sure that all the second derivative is going to be less than sk. Smaller the k, the better approximation. Less errors you may have. Okay, and the rest carries over the same. And let me show you another method which is better than those two methods. Better means it gives you a better approximation. Okay, but it will require more work. Not the best, but it's better than the previous two. Okay. Let me look for the name of it. I think it's called Simpsons. Simpsons. Now instead of chopping up into columns, and then we use 2 points at a time. This time we're going to use 3 points. Let me show you the idea of it. X right here, y right here. Say we have a function. This is f of x. Same setup. We want to approximate the area. We want to calculate the area bounded by of the region bounded by function f of x-axis from x equal to a, x equal to b. Now we have to jump it up into many columns as before. Okay. And instead of using 2 points, and then approximate the area of each column, now we're going to use 3 points. Let me use different color. Okay. And you know what? Whenever you have 3 points not in a straight line, you can always find a quadratic function, a parabola graph, go through 3 points. Okay. Okay. So 3 points. The first 3 points I can find the equation of a parabola to go through 3 points, and then the next 3 points right here, this first 3 points right here, the next 3 points right here, find another parabola, and so forth and so on. So the requirement for this method is what? The number n going to be even. N is even. In other words, we have to chop it up to an even number of columns. Okay. And let me skip the calculation. You guys can read it in the book. It's not long, but I just try to focus on the main thing that you guys are going to need to do the approximation. The first 3 points right here, we can always find the parabola function go through the 3 point. Okay, and the area for this region can be calculated as this. Approximately is what? Delta x over 3 times f of x0. I don't have to write that low. F of x0 plus 4 times f of x1 plus f of x2. Okay. The first column right here, now you have to think it's a big column right here. It's called like 2 columns. Okay, this area. This approximately calculate this. And then for the next one is what? From this is x0, right? x1, right? x2, right? So the next column is gonna be x2, x3, and x4. We use this right here. It's gonna be what? Delta x over 3 f of x2, 4f of x3, and f of x4. So far and so on, all the way to the end. And that's exactly why we need n. Number n going to be even, because it's odd. You cannot add them up. Okay, so Simpson rule say that the integral from a to b f of x dx is approximately equal to Sn, and you know what S stands for? Simpson, and n is the number of column. Requirement n is even. Okay. And how to calculate this? The first one is delta x over 3 f of x0 plus f of x1 4 times. I forgot number 4. 4 times f of x1 plus f of x2, right? And then you add with the next 2 columns, approximations delta x over 3 times f of x2 4 times f of x3 plus f of x4, and keep doing all the way to the end. Delta x over 3 what? F of xn minus 2 plus 4 times f of xn minus 1, and then plus f of xn. You add them all up. Okay? See what? You got delta x over 3 as a common factor. Delta x over 3 as a common factor. F of x1, 4f of x2, f of x2, plus another f of x2, so 2 times f of x2, and then 4f of x3, and then f of x4, another f of x4, so forth and so on. So this is the formula. Delta x over 3, f of x0 plus 4 times, oh, solve it just one f, okay, and then 4 times f of x1, and then 2 times f of x2, and then 4 times f of x3. Keep going, see 1, then 4, 2, 4, 2, 4, 2, all the way to the last one is just f of xn. The previous one going to be 4 times f of xn minus 1, okay? And that will be the formula. And the good thing about the Simpson method is this. The errors turn out to be way smaller than the previous 2 methods. But in here, you have to do 2 columns at a time. So a little bit more work. And to calculate the error, you have to calculate the derivative in the 4th power. Okay, and here's the error. error for the Simpson rule is error of the Simpson rule less than or equal to k times b minus a raised to the power of the fifth, and then all over 180 n to the 4. You see, this is the key. You have a 180. It's a bigger number, and right here not square anymore, raised to the 4. So the more you jump up, the more columns you have, the error turns out to be smaller pretty quick because you raised to the 4 power. And this is constant on top already. Okay. The thing is, the k right here is not for f second derivative anymore. This time you have to calculate 4 derivative of x, and then this one is going to be less than or equal to k. In here, I'm not going to give you the exact example, but I'll show you how to set up the formula. Okay. Say I got a function f of x, and then say n is going to be even. Right? How about n equal to 6? So I got what? x0 all the way to x6. Okay. Then 1, 2, 3, 4, 5, 6. So this is x1, x2, x3, x4, x5, x6. Of course, delta x is calculated as before. This is a right here. This is b right here. What? b minus a over 6 for delta x. Okay. Divided by 6. And the formula say what? Approximation of the integral from a to b f of x dx is approximately equal to S6 Simpson 6 column. What? Delta x. And then what do we have in here? F of x0, start with f of x0, and then what? 4 times f of x1, and then what? 2 times f of x2, and then 4 times f of x3, and then 2 times f of x4, and then 4 times f of x5, and then plus f of x6. You see? I went all the way from 0 to 6, x0, x1, 4 times x1, and 2 times fx2, 4 times fx3, and 2 times fx4, 4 fx5, and then just 1 fx6. You calculate. Depends on what the function is you plug in. And that was the idea. Okay. There's another type of problem that you may see, and this is what. Question is this. Say, if I want my error is no more than 0.0005, means what? This number is no more than, so less than or equal to 0.00001, so up to what? 5 decimal accuracy, and give you, say, k equal to 1, for example, make it easy. Okay, all those are constant. Can you calculate n to make the errors of approximation less than 0.001? Same. Another way of saying this is in normal languages, in everyday languages, this. How many columns do I need to jump so that my approximation of the error of that region with the accuracy up to 5 decimals? So you plug the formula, less than 5 point. K is a constant you know already, BA you know, and then 180 is constant already. You can solve for n from here, and you know exactly. And by the way, for the Simpson rule, make sure that you got n is an even number, okay? So say n gotta be greater than or equal to 19, you have to choose n equal to 20. Because you cannot do n19 for Simpson rule, but the other 2 rules, the midpoint and the trapezoid, and you can choose an even or odd number either way. And that was the idea. You see that in homework, they change the number, but this is a formula. It's just confusing in terms of phrasing it, but I explained it to you already, so it shouldn't be a problem. Okay, and let me stop this section right here. I'm going to move on to the next section. 7.8 improper integrals. Improper integrals. Basically, we have 2 types of improper integrals. The first type is this. Let me just draw the picture. Say you have a function, okay? And this is f of x. Let's go forever, go to infinity. And you want to integrate, say, from a to infinity of f of x dx. So in here I show you what you have a lower bound, a right here. Let's go forever. This is the area that you're looking for. Keep adding up forever. And sometime this area is gonna be this area right here, gonna be infinity. Means what? You add them up all the columns. It's approximation. Last time the sum is gonna be infinity. But many other times the area right here turned out to be a finite number. Which is the case we call what the integral is convergent. The other one goes to infinity. We say the area is or the integral is divergent. Okay. So how do you calculate? How do you take care of this problem? How do you calculate that integral? And the idea is this. We think of this as integral from a to say b f of x dx, and then we take the limit where b go to infinity. You see? So really we do the problems the same way as before, and after having the answer, we take the limit go to infinity. Okay. And that's called improper integral. And of course, same idea for the other way around. If you have, we learn by similarity, right? Say you have a graph like this. Let's say 2b right here, the integral from negative infinity to b of f of x. You know what to do with this. This is integral from a to b f of x dx, but this time we take the limit when a goes to negative infinity. Okay, same idea. We learn one, we know two. Okay, so this is the first type. All right, so let me give you an example of this, and then we can move on. Say, for example, f of x equal to 1 over x. Okay, so I want to calculate the integral from 1 to infinity of 1 over x dx. And I think of it as integral of 1 to, say, b or t, or whatever you call it, just a dummy variable, 1 over x dx, and I take the limit when t goes to infinity. Okay? And I'm going to do the integral, then I'll do the limit. The integral is what? 1 over x dx is ln of x, okay? Run from 1 to t, okay? This is, and don't forget that we have a limit in front, okay? T goes to infinity. This is what? Ln of t minus ln of 1, and then we have a limit t go to infinity. Ln of 1 is 0, so this is the limit of ln of t go to infinity, and this ln is go to infinity. So this integral is equal to infinity, and you said this integral is divergent. In other words, this area is going to be equal to infinity forever. It's going to be a very large number. Okay, but not all the case. Sometimes the areas turn out to be a finite number. We'll see this. Another example. Fixes the limit. F of x equal to 1 over x squared. I want to calculate the same thing, 1 over x squared dx, and I claim that this area will be a finite number. Take a look. Same idea right here, and square is and this is limit when t go to infinity of integral from 1 to t. This is x to the negative 2 dx. Now it's not ln anymore. It's going to be power rules applied. So add 1, x to the negative 1, negative of x to the negative 1. Okay. Run from 1 to t, and then take the limit when t go to infinity. Okay. And this is what? Negative 1 over t minus, with the minus become plus, negative 1, 1 over 1, so plus 1, and take the limit when t go to infinity, and you know what, t go to infinity, this equal to 0, so the limit is equal to 1. Okay, so really, this area is equal to 1. And you say what, this area is equal to 1, so the integral is convergent. Let me double check to see if my work is right. Yeah. Okay, that's the first type. But so I show you integral from a constant to infinity. By similarity, you can calculate this, apply the same idea. You can have what, integral from negative infinity to a constant, or even more general than that. If you have something like integral from negative infinity to positive infinity, okay, say the statistics function, you have something like this. Say, calculate integral from negative infinity to positive infinity. Just split it up to some point. It's equal to the integral from negative infinity to a constant a. Used to be able to choose 0 or 1 for a. Right? F of x dx, and plus integral from a to infinity, f of x dx, a somewhere. Okay, a is right here. Calculate the area from negative infinity to a, and then from a to positive infinity. And this one, take the limit when this one go to negative infinity, and this one take the limit when the point up there go to positive infinity. You add them up. So you have to do two limits to get to the answer. Okay? And that was the first type. And the second type is this. You may have some discontinuity in the middle of the function, or at the end of the function. So let me give you this example. Integral, the second type, okay? Type number 2. Discontinuity. Say integral f1 over x minus 3, x run from 1 to 3. Okay? You see what happened in here? You cannot plug an x equal to 3 in there. So let me graph this is hyperbola dx. This is what it is. This is the vertical line of the function. 3 right here. Use a different color, it gets stand out. The graph will look like this. Okay. And this is one right here. So integral from 1 to 3, you are looking for this area. And this is the vertical asymptote. You see what is the area right here, keep going forever. Okay. So how do you calculate this? Same idea, right? This is integral from 1, say, to t, 1 over x minus 3 dx, and then you take the limit when x approaches, when t approaches 3. T approaches 3. So, in other words, instead of calculating the integral from 1 to 3, we calculate the integral from 1 to t, and we move t closer and closer to 3. Okay, same idea as before. So you calculate this integral. What is it? This is ln of x minus 3, right? And run from 1 to t, and then take the limit when t go to 3. Okay, so this is ln of t minus 3 minus ln of 1 minus 3. You guys see how I have to put in absolute value because I want to make sure that the quantity inside ln is going to be positive. And then take the limit when t go to 3. This is ln of 2, right? Minus ln of 2, right here, constant. This is ln of t minus 3. And when t go to 3, it's going to be close to 0. And ln of 0, what is ln of 0? Negative infinity. So this is negative infinity. So absolute value is going to be positive infinity, right? So is that right? Yeah. So this is divergent. Yeah. So it doesn't have an answer. Lock that. And go to 0 positive. This is the log function look like. Yeah. This is ln. I think. Yeah. So when x go to 0 or t minus 3 go to 0, go to negative infinity. Okay. It's going to be a negative number because this area is below the x-axis. So it's going to be negative infinity. Negative infinity, and you say what? The integral is divergent. Okay. You don't have the answer. Make it a little bit more general. Say if you have, say, but I change this to 5. Now what? Number 3 is in the middle, right? So how do you take care of this problem? Oh, I changed the wrong number. This is minus 3. But now integral from 1 to 5. This is what I meant. Okay? So what? 1 right here all the way to 5 up here. 1, 2, 3, 4, 5. Same idea as before. You split it up into 2 integrals. Integral from 1 to 3, 1 over x minus 3 dx, plus integral from 3 to 5, 1 over x minus 3 dx. In other words, you're looking for this lower area right here, and then you calculate the upper area from 3 to 5 right there. Okay, this one is integral from